Hi, everyone. I'm Dale Kim. I'm the Senior Director of Technical Solutions at Hazelcast, and I'd like to talk about some of the initiatives that we're running with our big partners, IBM and Intel. As a quick agenda, I want to talk about the different deployment models that we're working on with these two big partners, and talk a little bit about the hardware aspects in working with Intel, and then quickly cover some of the use cases that are ideal for the combination of our technologies. So IBM clearly covers the infrastructural side with their Cloud Packs. So they're making a big push into cloud native deployments. So whether that's on premises or in a major cloud vendor. And they have a series of packs that are designed for different types of deployments based on applications, AI ops integration. The Cloud Pack that we're most interested in is the one for applications, especially since that's where our orientation is, around the notion of accelerating applications in a cloud environment. IBM is also pushing the notion of AI ops, so an emerging field around using artificial intelligence as a way of monitoring other complex systems and identifying the best optimizations to make to streamline their processes. And if we look at a quite complex diagram of an architecture in a cloud native environment with IBM. If you break it down, you'll see at the bottom the different cloud environments that you might want to run. And then all of this is based on Red Hat OpenShift, so a flavor of Kubernetes to run the applications. And then a lot of this has various components around the developer experience, the containers and predefined images. You'll see on the left is where Hazelcast fits in. So any of the applications that you'll deploy and leverage all these other components of this architecture, we fit in by enabling the in-memory store, providing transformations within our platform, and also the stream processing. So we apply across the board in any type of application you might want to deploy in this cloud native environment. There's also the story about the Edge, which is very interesting as an emerging type of deployment model. And we're one of the initial members of part of IBM's Edge ecosystem story, where they deployed the Edge Application Manager, which is a technology for managing software applications that are deployed out to the edge. And so if you think about some of these locations, like at manufacturing plants, on remote oil rigs, and connected cars, the administrative side of the software can be difficult, and that's what IBM provides with their Edge Application Manager, the foundation for being able to update and coordinate and monitor these Edge applications. And one of the tricky things about deploying in the Edge is the limited physical space that you have to deploy these software systems or hardware systems as well. So you're typically dealing with limited hardware footprint, smaller, more efficient CPUs, less memory. And so you need a software package that's optimized for that type of environment. And there's a lot of processing that can go on in the edge computing environment. So you can't necessarily use a simple package that runs on these edge devices. You want something that's pretty complex, but at the same time, fairly light. And so, for example, you might want to do some real-time processing, real-time analysis, deploy artificial intelligence modules to be able to make decisions on the fly at these remote locations. So for example, if you're dealing with a manufacturing plant where you're measuring the different aspects of the work in progress product, you want to be able to identify if there's some problem that will rise downstream as a result of some of the earlier patterns that you're reading. And so that will require some computing power, and having something like Hazelcast is ideal for that type of environment. Another side of the edge computing is you probably want to share a lot of the data you collect with some central data center. And so you can't generally send all of that data straight across the wire. So you have to do some kind of filtering, some kind of aggregation, some kind of summarization. And so you want to do that type of processing as well, so that you have a lighter payload when you send it over the network into your main data center. So having a software package that can do that as well for the holistic and analytics across all your different devices and all your different IoT sources would be important. So certainly it's also important to have a platform that's consistent across the board, from the edge to your public clouds, to your private data centers. And using Hazelcast, it's ideal for any of those types of environments. So when we talk about deploying it anywhere, it truly is lightweight enough to run in the edge, but it's powerful and scalable enough to run in a data center. And so you have that consistent platform in which you can share data, and it has the same foundation. So there's a lot of simplicity in the overall management. Mainframes are still a big part of today's business, and especially in some of these bigger, more established industries. And we're working closely with IBM in terms of how to get customers to get more value out of their mainframe systems. And oftentimes that simply means plugging in Hazelcast to provide new capabilities and new channels. So if you're thinking about stream processing or any type of web and mobile interface into the core data that's stored in the mainframe, you're not going to build the applications on the mainframes themselves. You use Hazelcast as that data layer that plugs into the mainframe. And as you do that, you can also deploy adjacent applications on your private cloud or in the public cloud. And you'll see with the green bar across that represents a unified data plane. With our WAN replication, you can copy that data across the different environments so that you have this consistent interface and that consistent experience for your end users, no matter where it's deployed, whether it's using mainframe data or some of the newer data that you might have in the cloud. So those are some of the use cases that combine IBM's software stack with our application acceleration technology. And I want to talk a little bit more on the hardware side. So we're part of a program that Intel put together in pushing their new Optane technologies. And Optane is really fascinating in the sense that it covers different use cases depending on how you deploy it. It can be used as a great alternative to DRAM, but also as a very fast SSD. And the way we like looking at it is primarily as that volatile memory store. And so I say this is more scalable than DRAM or faster than SSDs. And I say or because it's an either or in terms of how you deploy it. You can't deploy it one way where you'll get more scale than DRAM and faster than SSDs. So that's an important distinction to make. But in this chart, you'll see some of the price differentials that you'll see that for DRAM today, for 128 gigabyte DIMM, about $4,500, and for Optane PMem, about $1,800. And so if you go to the higher scale, around 1 terabyte per server, then you'll see quite a stark difference. And so as you're building out these higher density, RAM dense servers, you can deploy fewer of them, which means less network traffic, more data to store in memory, and get the advantage of that in-memory speed. So here's just a quick chart of some of the benchmarks that we've run. So for this simple benchmark, we just did a load with 50% reads and 50% writes. You'll see the circle represents the comparison of red versus blue, where red is the DRAM and blue is Optane. And so the performance characteristics are relatively same for very small object sizes. And so we're here seeing 1.8 million operations per second. And then as the object sizes, as part of a key value store lookup, if the object sizes are a little bit bigger, that's where you'll see a little bit of performance degradation, which is natural for this type of environment. But you'll see that there's the brownish color for Optane, and then there's a lighter gray that fluctuates a bit. But you're seeing approximately the same performance between DRAM and Optane. So one thing to note is that if you compare them straight out in a simple read-write test, DRAM is going to win, but it's the distributed environment which obscures some of the performance differences so that the overall performance will look very identical. And that's one of the advantages of being able to use it in a DRAM alternative use case. And so we've made some improvements along the way in working with Intel. One of our later versions of Hazelcast, we ran some benchmarks, and you'll look at the numbers between DRAM and the 4.1 version of Hazelcast, and you'll see the operations per second are very identical, very close, which means that if you're looking to scale up and use a lot more data for in-memory lookups, then Optane is a very attractive technology to use as part of your fast applications. And so the volatile memory usage of Optane is one aspect. So on a completely different level, we can also use Optane as a faster SSD. And so we have this notion of persistence where a lot of the data that we have is going to be primarily accessed in memory. But for the purpose of durability, we can enable what's known as a hot restart store. So we'll persist that to the disk. And it's faster to read the pre-indexed disk in its format from a local node versus reading it from the original system of record. So having this hot restart store is very advantageous if you have a mission critical system that can't suffer a lot of downtime. So should you shut down a system for maintenance or experience some type of failure, you can read back from that hot restart store, and using Optane allows you to get that memory populated again so that node is quickly up and running. And so one of the use cases that we're working with IBM and Intel on involve this notion of on-demand analytics. And other people refer to it as real-time analytics, where you're getting some stream, you index it, populate it, and then end users can do some querying on it. But you'll see from this model that a lot of times that real-time environment is hard to do because of the latency they experience in indexing data. So someone might ask, well, why can't you just store all of this data in a big data warehouse, do all the appropriate indexing? The problem is that with all the different types of queries that you want to run, you'll have many different types of indexing and indexes. And so with all the different types of indexes, that takes time. And most of these expensive data warehouses can only handle that with extreme hardware investment. And so the alternative to that is, what if you could just simply take the data from that input queue or from the data storage mechanism, and then on demand, based on a user query, only read the data that's relevant to that query, index it in real time or near real time, and then dump it into a repository where you can do additional drill down analytics. And that's the model that we're creating. So there's this big dependency on the cloud native to be able to scale out, as well as the high-end servers with dense memory, so that you can store a lot of that analytical data as a fast repository in Hazelcast. And this is what the architecture looks like. It's fairly straightforward, where Hazelcast is managing the ingest from the data sources. There's a user interface to accept a query, and based on that, that's where the on-demand part comes in. The ingestion side of Hazelcast will determine what data will be pulled in. It'll index it, and it'll send it out to our in-memory store that interfaces with a web server for the purposes of the drill down analytics. At the same time, you can also read in the real-time data as it comes in, do some processing, and store it in memory as well. So you have a combination of that raw data that you're processing, as well as aggregated data that you're processing based on the user query. So a lot of processing can be done here. It looks like a typical stream processing engine might be able to do that. But if you're thinking about running an on-demand query, you might be dealing with several terabytes of data, and you want to be able to index that as fast as possible. You don't want to wait an hour before you're ready to query. And that's where Hazelcast's performance advantage will help, where you can index all that quickly so that after you submit that query, you're ready to do some additional querying and drill downs into your data right away. And these are some architecture diagrams that just talk about the different ways you can scale. I think I'm running out of time, so I'll just briefly talk about this in the context of how you can scale out. You can have the streaming side of Hazelcast scale alongside the in-memory store. So you can use those as one group that scales out. Or you can scale out the ingestion side independently of the in-memory store. So with the architecture, you have that flexibility depending on where some of the bottlenecks might lie in your pipeline. And the final thing I want to talk about is payment processing. And so with a lot of the banks that we talk to, they'll have the channels on their left that represent the core banking, and those represent the legacy infrastructure that they don't want to mess with. They don't want to touch it. They don't want to make any changes, and they just want to plug in something as a data layer to handle some of these new capabilities. And for payment processing, the model is very similar. So when companies are deploying web and mobile applications, using Hazelcast as a great intermediary data layer. For something like payment services, where you're doing a lot of processing like fraud detection, authentication, and network selection, and you have to look up historical data, you can use Hazelcast for both its stream processing and its in-memory storage to be able to determine whether a transaction is legitimate and whether it should move forward, and then interface with the different payment providers to help complete the transaction. So all of this can be self-contained, run in the cloud, and done in a way that's fast enough to be able to support the huge volumes of payment processing transactions that banks are experiencing today.